Have you ever tried to picture a world where not one, not two, but 6 suns hang in the sky? Imagine stepping outside and seeing a horizon ablaze with light from multiple stars, each casting its own glow, creating sunrises and sunsets that would seem like something out of a dream. For most of human history, such a place existed only in science fiction. But what if I told you these extraordinary systems are not only real, they're hiding secrets that challenge everything we thought we knew about how stars form and behave? Welcome to the mind-bending reality of sextuple star systems, cosmic rarities so complex and strange that even astronomers are left in awe. In a universe filled with wonders, these multi-star arrangements stand out as some of the most peculiar architectures nature has ever devised. We're talking about not just double or triple stars, but 6 massive bodies locked in an intricate gravitational dance, orbiting one another in patterns so precise and delicate that a single misstep could send the entire system spiraling into chaos. The sheer improbability of such a configuration existing, let alone surviving for millions of years, defies our basic understanding of cosmic mechanics. It's like a perfectly choreographed ballet performed on a scale so vast, it stretches the limits of both imagination and physics. And that's exactly what we're diving into today. 30 of the strangest, most fascinating discoveries scientists have made about these celestial marvels. From stars that eclipse each other in mesmerizing cycles to gravitational puzzles that rewrite the rules of orbital dynamics, each finding pulls back the curtain on a deeper layer of mystery. This is more than just a tour of unusual astronomical phenomena. It's a journey to the edges of known science, where every discovery raises new questions and every answer only deepens the wonder. So settle in and open your mind to the extraordinary, because what you're about to learn might just change how you see the night sky forever. But before we can appreciate just how bizarre these systems get, we have to start at the beginning with the discovery that opened our eyes to their very existence. For centuries, anyone looking up at the constellation Gemini would recognize one of its brightest points of light, the star known as Castor. To the naked eye, it appeared as a single, brilliant beacon. Even through the earliest telescopes, it presented itself as a stunning double star, 2 luminous companions orbiting one another, a fascinating sight, but one that astronomers felt they understood. The truth, however, was hiding in plain sight, a cosmic secret waiting for the right technology to reveal its depths. That revelation began not with a bigger telescope, but with a more precise one. By breaking the light from these stars into its constituent colors through spectroscopy, astronomers detected something extraordinary. Each of the 2 stars they thought they were seeing was in fact not a single star at all, but a pair of stars so close together that their light blurred into one. The telltale sign was in the starlight itself. The spectral lines, the unique fingerprints of chemical elements, were Doppler shifted, wobbling back and forth as the stars in each tight pair rapidly orbited their common center of mass. This technique unveiled Castor A and Castor B, each as spectroscopic binaries, bringing the count from 2 stars to 4. The story didn't end there. Astronomers soon noticed a faint, distant companion star circling the main group, which they named Castor C. Applying the same spectroscopic analysis to this dimmer member, they discovered the same astonishing pattern. Even this remote outpost was not a single star, but another fiercely close binary pair. What was once a bright point of light, then a double, was now definitively confirmed as a system of 6 stars, 3 pairs of binaries, all gravitationally bound in an intricate celestial hierarchy. This realization was a complete paradigm shift. It forced us to move beyond simple categories of single, double, or even triple stars and into the far more complex realm of higher-order multiples. The existence of Castor proved that stars could form and remain stable in configurations of mind-boggling complexity, a nested system of orbits within orbits. It was the first confirmed sextuple, a gravitational masterclass that forever changed our classification of star systems and hinted at the incredible architectural diversity the universe is capable of building. This layered arrangement, known as a hierarchical orbit, is the only way such a complex system could possibly remain stable over astronomical timescales. It's a cosmic concession to the laws of physics, a way to manage the unimaginable gravitational chaos that would ensue if all 6 stars tried to orbit a single common point. Instead, the stars sort themselves into a celestial pecking order, a series of smaller, stable dances contained within a much larger and slower one, like a set of Russian nesting dolls where each doll is a perfectly balanced orbital pair. At the very heart of the system, you'll find the tightest and fastest dancers. These are the innermost binary pairs, 2 stars so close they whirl around each other in a matter of days or sometimes even hours. Their gravitational bond is incredibly strong, and from a distance, this frantic waltz makes them appear as a single, stable point of mass. This is the first and smallest doll in our set. The next layer out involves another binary pair, but this one orbits at a much greater distance from the first. They don't orbit the individual stars of the inner pair, but rather the combined center of mass of that entire first binary system. This creates a stable quadruple system, 2 pairs endlessly circling one another in a slow, graceful courtship that can take decades or even centuries to complete a single orbit. But the true marvel of a sextuple system is the addition of the final, outermost layer. The third binary pair, often separated by distances thousands of times greater than the gap between the inner stars, enters into an immensely wide orbit around the central quadruple group. This final dance is the slowest and most stately of all, a single revolution that might take many thousands of years. This hierarchical structure, with its distinct tiers of motion, is what keeps the entire system from tearing itself apart through gravitational interference. The stars effectively simplify their own complex relationships. From the perspective of the distant third pair, the frantic activity of the inner 4 stars averages out into a single, predictable gravitational anchor. This orbital architecture forces us to completely abandon the simple, 2-body equations that once defined celestial mechanics. Predicting the motion within a sextuple system requires grappling with an n-body problem of nightmarish complexity, where every single star exerts a gravitational pull on every other star, all while moving in multiple directions at once. It's a dynamic, living puzzle that challenges our most powerful supercomputers, pushing the very limits of our ability to model and understand the cosmos. The existence of these systems is a breathtaking demonstration that the universe is not only capable of building immense complexity, but of structuring it in a way that endures for eons. Perhaps the single most baffling discovery about these intricate stellar families is their profound longevity. Given the sheer gravitational complexity at play, with 6 massive bodies all pulling on one another, you would expect these systems to be cosmic ticking time bombs, destined to fly apart or collapse into a chaotic disaster within a relatively short period. Yet, the observational evidence points to the exact opposite conclusion. These sextuple systems aren't just stable for a few million years. Many have likely existed in this harmonious state for billions of years, persisting across time spans nearly as long as the universe itself. This presents a monumental puzzle for astrophysicists, forcing a complete re-examination of what we thought we knew about orbital mechanics on a grand scale. So how do they achieve this impossible-seeming feat? The secret lies in nature's ingenious application of precision engineering on a cosmic scale. Astronomers have discovered that these systems don't just happen to be stable by chance, they are mathematically fine-tuned marvels. The key is found in the concept of orbital resonance, a delicate and harmonious relationship between the orbital periods of the different pairs. It's not unlike the precise ratios that create beautiful harmonies in music. For instance, the innermost binary might complete exactly 3 orbits in the time it takes the next binary pair to complete 2 orbits. These resonant relationships act as a gravitational metronome, synchronizing the motions of the stars and preventing their pulls from ever falling into a destructive, chaotic rhythm that would disrupt the entire system. Furthermore, the distances between these stellar pairs are not arbitrary. They are carefully balanced, existing within a very specific and narrow Goldilocks zone. If the outer binary orbited just a little bit closer, its gravitational tugs would be strong enough to perturb the delicate dance of the inner quadruple system, eventually destabilizing it. If it were much farther away, the gravitational bond would be too weak, and the third pair would simply drift off into space, never to return. The fact that we find these systems at all means that each one has miraculously found its perfect, balanced configuration, a celestial sweet spot that allows for eternal coexistence. This discovery is so much more than just an astronomical curiosity. It strikes at the very heart of a problem that has plagued physicists for centuries. The infamous N-body problem, which states that it is fundamentally impossible to predict the precise long-term motions of 3 or more bodies interacting through gravity using a simple formula, is a cornerstone of chaos theory. For 3 bodies, the problem is already notoriously difficult. For 6, it should be utterly intractable. Yet, these sextuple systems are living proof that nature has somehow found hidden solutions to this problem. They are not chaotic, they are profoundly ordered, demonstrating that stability can emerge from unimaginable complexity through the elegant application of mathematical rules we are only just beginning to comprehend. If you thought 6 stars were the limit of cosmic creativity, just wait until you discover what's dancing among them. For years, the scientific consensus held that the gravitational turmoil within a multi-star system would be far too violent, far too unpredictable to allow for the gentle, gradual process of planet formation. The primordial disks of gas and dust that give birth to worlds, it was thought, would be shredded and scattered by the competing pulls of so many stellar hosts. The very idea of a stable, enduring orbit in such an environment was considered almost laughable. Yet, once again, the universe had a surprise in store, forcing us to rewrite the textbooks with the stunning discovery of planets thriving in these sextuple systems. These aren't just any planets, they are real-world analogues to the most famous fictional world in science fiction, Tatooine from Star Wars, where a young Luke Skywalker watches a double sunset. But the reality is infinitely more spectacular. Imagine standing on the surface of a world where your sky is adorned not with 2, but with 3 pairs of suns. Some would appear as brilliant, close-set twins, while others would hang farther apart like dazzling jewels. And because the stars in a sextuple system often vary in type, from blazing blue giants to cooler orange or red dwarfs, the sky would be a kaleidoscope of different colored lights, casting ever-changing, multi-hued shadows across the landscape. The concept of day and night itself would become fluid, with some stars potentially never setting at all, creating a perpetual, ethereal twilight. The existence of these planets is a direct affront to our previous understanding of orbital stability. How can a world possibly find a safe path around 6 moving gravitational targets? The answer appears to be both simple and ingenious: distance and hierarchy. These circumsextuple planets, as they're called, don't attempt to weave dangerously between the interstellar pairs. Instead, they follow a remarkably wide, sedate orbit around the entire system's common center of mass. From this vast distance, the complex gravitational pushes and pulls from the 6 individual stars average out into a single, steady, and predictable force, almost as if the planet is orbiting one very massive object. It's a masterclass in cosmic simplification, where the planet only feels the collective gravity of the stellar family, not the chaotic individual tugs. This doesn't mean the environment is perfectly serene. The planet would still experience subtle gravitational nudges, tiny perturbations that could, over millions of years, potentially alter its orbit. This is where the same principle of resonance that stabilizes the stars themselves likely comes into play for the planets. Astronomers hypothesize that these worlds have settled into orbital resonances with the stars, their year-long journey around the system synchronized in a precise mathematical ratio with the orbital periods of the stellar pairs. This harmonic relationship acts as a protective rhythm, gently shepherding the planet and preventing its path from drifting into a danger zone. Finding such a planet was like discovering a single, perfectly balanced marble rolling on a giant, moving platter held by 6 dancers, a testament to nature's astonishing ability to find order within apparent chaos. The implications for the hunt for habitable worlds are profound. We once believed that life could only arise in the quiet, predictable neighborhood of a single star like our Sun. The discovery of planets in sextuple systems dramatically expands the cosmic real estate we consider potentially habitable. It suggests that even in the most dynamically extreme environments, nature can carve out a stable niche where the conditions for life might take hold. While the constantly shifting stellar radiation would present unique challenges for any potential biology, it also opens the door to possibilities we are only beginning to imagine. The universe, it seems, is far more inventive and far more welcoming than we ever dared to dream. And if you think the orbital dynamics are complex, just wait until you see the light show. From our vantage point on Earth, some of these sextuple systems are positioned in such a way that their orbital planes are nearly edge onto our line of sight. This creates a celestial phenomenon on a scale so bewildering it initially had astronomers double-checking their equipment for errors. We're talking about eclipses, but not the singular, predictable kind we experience with our Moon and Sun. In a system with 6 stars moving in multiple, overlapping orbits, the eclipses are constant, overlapping, and breathtakingly intricate, producing a pattern of dimming and brightening so bizarre that the resulting data, called a light curve, looks less like a scientific measurement and more like the chaotic readout of a malfunctioning machine. The star system TIC 168769088 is a perfect mind-bending example. This isn't just a star that dims and brightens, it's a full-time cosmic lighthouse with a broken switch. When astronomers first analyzed its light curve from the TESS spacecraft, they witnessed not 1 or 2, but dozens upon dozens of distinct dips in brightness. There were deep, pronounced eclipses where one star completely blocked another, shallow dips where a star only grazed the limb of its companion, and even strange V-shaped dips hinting at complex gravitational interactions warping the stars themselves. Over a single, complete orbital cycle for the outer stars, a period that itself can last for years, the inner pairs are whirling around so fast that they create their own rapid-fire series of eclipses, all superimposed on top of the slower, grander eclipses of the wider pairs. The final result is a light curve of almost incomprehensible complexity, a tangled web of shadows that requires immensely powerful algorithms to even begin to untangle. Decoding this flickering signal is like trying to listen to 6 different songs playing all at once from a single radio, and then trying to identify every instrument in each band. Each dip in light holds a wealth of information. The depth of the eclipse tells us about the relative sizes of the stars involved. The duration of the dip reveals the orbital speed. The shape of the curve can even indicate the surface temperature of the eclipsed star and whether it has sunspots or other surface features. For astronomers, this isn't just noise, it's a golden opportunity. This constant dance of shadows provides the most precise data possible for measuring the physical properties of the stars, their masses, diameters, temperatures, and shapes, with an accuracy that would be utterly impossible if we were observing them in isolation. The very chaos of the light curve is what allows for this unprecedented level of detail. The most fascinating insight from this flickering comes from what's known as the O'Connell effect. In simpler binary systems, the 2 peaks of light in a light curve representing when the largest surface areas of the stars are facing us are usually identical in brightness. But in these complex systems, the peaks are often starkly different. One might be significantly brighter than the other. This asymmetry is a direct window into the violent gravitational environment these stars endure. The immense tidal forces from having so many close companions can distort the stars from perfect spheres into egg-shaped ovals, making one hemisphere permanently larger and brighter than the other. Furthermore, these forces can trigger massive star spots like sunspots but on a colossal scale, and intense magnetic activity that alters the star's brightness. The light curve, therefore, becomes a living record of not just orbits, but of the physical distortion and stellar fury happening in real time. Now, consider the invisible forces at play within this stellar ballet, an electromagnetic environment so extreme it defies earthly comparison. Each of these 6 stars is not just a ball of hot gas. It's a powerful, dynamic magnet, generating a complex magnetic field that extends far out into space. In a single star system like our own, this field creates a relatively orderly bubble known as a magnetosphere. But in a sextuple system, you have 6 of these magnetic bubbles, all of different sizes and strengths, constantly inflating, deflating, and violently colliding as the stars whirl around one another. The result is a permanent, cosmic-scale electromagnetic storm, a tangled web of magnetic field lines that snap, reconnect, and unleash unimaginable torrents of radiation. The sheer diversity of stellar types in these systems makes this magnetic mayhem even more potent. A hot, massive blue giant star might have a fierce but relatively simple magnetic field, while a cooler, smaller red dwarf could possess a magnetic field thousands of times stronger, prone to violent flares and eruptions. When these vastly different magnetic personalities are forced into a close gravitational relationship, their fields don't just gently push against each other, they clash. The field lines from one star get twisted and wrapped around another, storing up immense energy like a colossal rubber band being stretched to its limit. Eventually, this energy has to be released, triggering a magnetic reconnection event, a stellar explosion that unleashes a supercharged blast of X-rays and gamma rays across the entire system. This creates a radiation environment that is, without exaggeration, instantly lethal. Any hypothetical planet forming in the system's habitable zone would be periodically sterilized by these blasts, its atmosphere stripped away and its surface bombarded by radiation that would shatter complex molecules. Life as we know it could not survive this onslaught, yet from a purely observational standpoint, this chaos creates a phenomenon of terrifying beauty. These particle storms, channeled along the complex magnetic highways between the stars, would generate auroral displays on a scale we can scarcely imagine. Instead of a gentle green glow over a planet's poles, picture entire worlds illuminated from pole to pole in shifting, violent hues of purple and red, with luminous arcs of energy visibly connecting one star to another in the sky, a permanent celestial light show powered by the system's relentless magnetic fury. This intricate gravitational dance does more than just create a spectacular light show. It fundamentally alters the very nature of the stars themselves, forging stellar oddities that simply shouldn't exist. In the relative peace of a single star system, a star's life follows a well-understood path, its fate determined primarily by its initial mass. But place that same star into the gravitational pressure cooker of a sextuple system, and the rules go out the window. The constant, close proximity tug of war between stellar siblings creates an environment ripe for producing cosmic chimera stars that break all the standard classifications and force us to reconsider the textbook model of stellar evolution. One of the most common and puzzling anomalies found in these systems is the blue straggler. Imagine a stellar retirement home where all the residents are old, cool, red stars, but right in the middle of them is one vibrant, hot blue star that looks impossibly young. According to our models, all the stars in a cluster or a bound system should have formed at roughly the same time. the more massive stars burn through their fuel quickly and die young, leaving behind the slower-burning, lower-mass stars. A blue straggler is a glaring violation of this rule. It's a star that appears rejuvenated, shining with a blue-hot intensity that its neighbors lost eons ago. For decades, the existence of blue stragglers was a major headache for astronomers. How could a star suddenly get a new lease on life? The answer, it turns out, is hidden in the chaotic dynamics of multi-star systems. In the crowded core of a sextuple system, stars can literally collide and merge. Two older, lower-mass stars might be thrown together by a gravitational slingshot, combining into a single, more massive and hotter star, a stellar Frankenstein's monster that appears younger and bluer than it has any right to be. Alternatively, one star in a tight binary pair can act as a vampire, using its gravity to siphon fresh hydrogen fuel directly off the surface of its companion. This stolen fuel replenishes its outer layers, reigniting nuclear fusion with a new intensity and causing it to blaze blue once more. In a sextuple system with so many stars in such complex orbits, these dramatic events are not rare occurrences. They are a fundamental part of the life cycle. Beyond blue stragglers, these systems are also factories for chemically peculiar stars. A star's surface chemistry is usually a direct reflection of the cloud of gas from which it formed. But in a sextuple system, the surface can become a bizarre and unpredictable chemical laboratory. The powerful magnetic fields we discussed can create strange zones on a star's surface where certain elements like iron, chromium, or rare earth elements become mysteriously overabundant while others seem to sink out of sight. These aren't uniform changes. They can create stark chemical spots, like a patch of the star's surface that is essentially made of mercury or manganese. The leading theory for this phenomenon points again to gravitational settling and radiative levitation. In a quiet star, gravity pulls all elements downward equally, and radiation pressure from the core pushes them all upward. But in the turbulent, magnetically charged environment of a close stellar partnership, this balance is shattered. For some elements, the lift from radiation can overcome gravity, causing them to float to the surface in concentrated patches. For others, the strong magnetic field can trap them in specific regions, preventing them from mixing back into the star. The result is a stellar surface with a chemical composition that defies the standard cosmic abundance, a direct and visible testament to the extreme physics at play. Perhaps the most profound implication is that this gravitational interference might actually alter a star's core evolution. The standard clock of a star's life is set by how quickly it consumes the hydrogen in its core. But in a system where stars are constantly tidally distorted, spun up, or mixed by gravitational interactions, that fuel might be stirred or replenished from the outer layers. This could potentially slow down the aging process or trigger unusual and premature evolutionary phases. We might find a star that has the mass of a main sequence star but the radius and temperature of a much older subgiant, or a star that's pumping out far more helium than its age would suggest possible. These aren't just weird stars, they are living experiments showing us that the path of stellar life has many more branches and possibilities than we ever imagined, all fostered by the incredible complexity of a sextuple star system. But the drama of these systems isn't confined to the light we can see. It extends into the very fabric of the universe itself. Every movement, every orbital dance within a sextuple star system sends ripples out across space-time, vibrations in the cosmic medium known as gravitational waves. For most of astronomy's history, these waves were a purely theoretical concept, a prediction of Einstein's general relativity that seemed almost too faint to ever detect. But with the advent of observatories like LIGO and VIRGO, we've begun to listen to the universe in this whole new way, and the complex choreography of these 6 star systems makes them some of the most prolific and fascinating gravitational wave factories in the cosmos. What makes them so special is the sheer range of motion happening all at once. Unlike a simple binary system that produces a gravitational wave at a single, pure frequency, a steady hum, a sextuple system is a full orchestra. The innermost ultra-tight binary pairs whirl around each other at incredible speeds, completing orbits in just hours or days. This frantic motion generates a high-frequency gravitational wave signal, a kind of cosmic piccolo, shrill and fast. The next binary pair out orbits on a much slower timescale, perhaps taking years to complete a single loop. Their gravitational wave signature is a lower, cello-like tone, a steady thrum underlying the piccolo's melody. And finally, the outermost, widest pair moves at a glacial pace, their orbital period stretching across millennia. Their contribution is the deepest, most profound bass note imaginable, a fundamental frequency so low that it's virtually inaudible to our current detectors. The combined effect is a gravitational chord, a complex symphony of space-time vibrations with multiple notes playing simultaneously. This isn't just noise, it's a rich source of information. By learning to untangle this chord, to identify each individual instrumental line within it, astronomers can reconstruct the entire architecture of the system without ever seeing a single photon of light. The frequencies tell us the orbital periods, the amplitudes reveal the masses of the stars, and changes in the signal over time can even hint at the slow orbital decay as energy is radiated away in the form of these very waves. It's the ultimate test of Einstein's theory, pushing his equations to their absolute limit in an environment of unimaginable gravitational complexity. The potential for discovery here is staggering. Future space-based gravitational observatories like the planned LIS mission will be specifically tuned to listen for these lower frequency waves emanating from systems just like these. By monitoring a sextuple system for decades, we could witness general relativity in action with a precision that laboratory experiments on Earth could never hope to achieve. We could look for subtle deviations from Einstein's predictions, potential hints of new physics hiding within the gravitational extremes of these systems. It transforms these distant families of stars from mere curiosities into fundamental laboratories, allowing us to use their intricate motions to probe the deepest laws governing space, time, and gravity itself. This brings us to one of the most head-scratching discoveries in these systems, a finding that seems to break one of astronomy's most fundamental rules. When we look at a star cluster or a multi-star system, we operate on a core principle. All the stars within it were born from the same collapsing cloud of gas and dust, meaning they should all be the exact same age. It's a stellar family with siblings that have shared a life from the very beginning. But when astronomers applied standard dating techniques to the individual stars within some sextuple systems, the results were utterly baffling. The stars didn't show a single, coherent age. Instead, the system looked like a chaotic family reunion with members from completely different generations, with some stars appearing billions of years younger than their closest companions. This age discrepancy isn't just a minor calculation error. It's a direct challenge to our understanding of stellar physics. The primary method for estimating a single star's age is to place it on the Hertzsprung-Russell diagram, which plots a star's brightness against its color or temperature. A star's position on this diagram tells us what stage of life it's in. A massive, hot blue star sits on the main sequence, burning hydrogen in its core, and its precise location tells us how long it has been doing that. Once it exhausts that fuel, it evolves off the main sequence, becoming a red giant or subgiant. By charting this evolutionary path, we can pin down a star's age with reasonable accuracy. But in a sextuple system, this clean timeline falls apart. You might have one star that sits right where it should be for a system age of 10 billion years, while its binary partner, with a nearly identical mass, is blazing away as if it's only 2 billion years old. It's as if you found a medieval knight standing next to an astronaut and they claimed to be twins. So what's really going on? The answer lies not in a flaw in our dating methods, but in the radically transformative power of the system's gravitational environment. Those standard models for stellar aging assume a star lives a quiet, solitary life, its evolution governed solely by the slow and steady burn of its internal fuel. But a star in a tight sextuple system lives a life of constant gravitational intervention, and this dramatically alters its appearance and life cycle. The most common culprit is mass transfer, a process where one star literally feeds on another. In a close binary pair, if one star evolves slightly faster and expands into a giant, its outer atmosphere can be pulled away by the gravity of its companion. The receiving star gains a massive influx of fresh, hydrogen-rich fuel. This sudden donation rejuvenates it, making it hotter, bluer, and brighter, effectively resetting its evolutionary clock and making it appear drastically younger than it truly is. Another dramatic rejuvenation process is a full stellar merger. The complex dance of three or more bodies can sometimes destabilize orbits, resulting in two stars colliding and merging into one. This new combined star is more massive than either of its progenitors. Since massive stars burn hotter and brighter, this new entity will instantly look younger and more vigorous than its unchanged siblings. It's not actually younger, it's a completely new stellar entity that just started its life, even though the materials it's made from are as old as the rest of the system. This creates an impossible-seeming age gap within a single family. Beyond these violent events, the constant gravitational tides also play a subtler but equally important role. A star being tidally locked and stretched by its companions experiences intense internal friction. This churns and mixes the star's interior, bringing fresh hydrogen from the outer layers down into the core and stoking the fires of nuclear fusion. This mixing can significantly extend the star's time on the main sequence, making it look youthful and vigorous long after a star of the same mass and age in isolation would have started to fade. The star isn't cheating death, it's just having its fuel supply managed far more efficiently by the gravitational forces acting upon it, presenting itself as a vibrant outlier in an otherwise ancient system. Now, if you thought gravitational chaos and impossible ages were strange, wait until you get a look at the chemical recipes brewing inside these stars. When astronomers point their spectroscopes at the individual members of a sextuple system, they often find a cosmic chemistry set that defies all logic. Instead of showing the universal abundances, we expect a familiar mix of hydrogen, helium, and trace amounts of heavier elements. Some of these stars display surfaces bizarrely rich in specific, rare elements like mercury, manganese, platinum, or europium, while their immediate binary partners, stars that formed from the exact same cloud of gas, show perfectly normal solar-like compositions. It's as if one sibling decided to season their surface with a rare cosmic spice, while the other ate a completely plain meal. This isn't a subtle difference, it's a glaring anomaly that points to processes of elemental sorting and purification we simply don't see anywhere else in the universe. This phenomenon creates what are known as chemically peculiar stars, and they are almost exclusively found in the tight binary pairs within these complex systems. The leading theory to explain this cosmic alchemy involves two powerful forces: intense magnetic fields and the subtle but persistent push of radiation. In a typical, isolated star, gravity pulls all elements downward with equal force, while the torrent of radiation streaming from the star's core pushes outward. For most elements, gravity wins and everything stays mixed, but in the magnetically charged, turbulent environment of a close stellar binary, this balance is completely upended. For certain elements, the outward pressure of radiation can actually overcome gravity, levitating them to the surface. Meanwhile, other elements sink out of sight, creating a stratified surface layer that's completely unlike the star's interior. The strong, often distorted magnetic fields present in these systems act like a giant sorting filter, trapping these levitated elements in vast, concentrated patches on the stellar surface. Imagine a star with a continent-sized spot on its surface that is essentially pure mercury or gallium. This isn't just a theoretical idea, we have observational evidence for it. The light from these stars changes in a specific, periodic way as they rotate, because we're alternately seeing the chemically normal side of the star and then the bizarre, element-rich patch. It's a direct signature of a stellar surface that is not uniform, but rather a patchwork of extreme and unnatural chemistry, all orchestrated by the unique physical conditions that only exist in these multi-star pressure cookers. This process, known as radiatively driven diffusion, is slow and delicate, requiring a remarkably stable environment to work, which is the final great irony. It seems the very same gravitational chaos that can cause stellar collisions and mass theft is also capable of creating pockets of incredible stillness. In some of these tight binaries, the stars are tidally locked, their rotation synchronized with their orbit, creating a zone of gravitational calm right at the point where the magnetic field is strongest. This strange tranquility amid the orbital frenzy provides the perfect laboratory for this slow elemental sorting to occur over millions of years, allowing these stars to become cosmic refineries, purifying and concentrating elements in a way that should be impossible. It's a stunning demonstration that from great chaos can emerge exquisite order, and that the universe's recipe for building stars is far more complex and inventive than we ever imagined. And just when we thought these systems couldn't get any stranger, astronomers stumbled upon a signal so bizarre it briefly made them question whether they were listening to nature or something else entirely. It began with the detection of unexpected, powerful radio emissions emanating from several known sextuple systems. These weren't the predictable, steady radio waves produced by stellar winds or the gentle hum of a star's corona. These were intense, coordinated bursts of energy, pulsing across multiple radio frequencies in a pattern so structured and complex that it stood out from every other known type of stellar radio signal. For a thrilling and nerve-wracking moment, the possibility hung in the air that these patterns were not natural at all, sparking whispers of a detection that would change everything. The initial data was unlike anything in the catalogs of stellar phenomena. Imagine tuning a radio and hearing what sounds like a frantic, repeating sequence of bursts, a series of rapid pulses in one frequency band, immediately echoed by a deeper, slower pulse in another band, all while a third, continuous tone warbles in the background. This coordinated symphony across the radio spectrum didn't match the chaotic crackle of solar flares or the steady spin of pulsars. The timing between some of the bursts showed hints of mathematical regularity, a hallmark that often makes astronomers' hearts race with the potential implication of an artificial source. It was a classic signature that, in the world of science fiction, would be the first hello from an advanced civilization. The Discovery team had to rigorously follow the protocols established for such a finding, methodically ruling out every possible natural explanation before even daring to entertain the extraordinary. The true explanation, once uncovered, turned out to be far more fascinating than mere aliens. The culprit was a previously unknown astrophysical process born from the unique marriage of powerful magnetic fields and complex orbital mechanics. The coordinated bursts were a natural lighthouse effect, but one of immense complexity. Here's how it works. In these systems, the magnetic fields of stars in the tight inner binaries are constantly being wound up like colossal springs by their rapid orbital motion. This stores a tremendous amount of energy. When these fields inevitably snap and reconnect, a process known as a superflare, they don't just release energy in a single blast. Instead, the explosion injects a huge cloud of ultra-relativistic electrons into the magnetosphere, a cloud that then gets caught in the magnetic fields of the other stellar pairs. This is where the coordination comes in. As this cloud of high-energy particles spirals along the magnetic field lines connecting different stars, it generates radio waves. But the frequency of the radio emission depends on the strength of the magnetic field it's passing through. A journey through the intense field near a red dwarf produces a high-frequency burst, while a moment later, the same cloud might be channeled into the weaker field of a more distant giant star, generating a low-frequency pulse. The orbital motion of the stars themselves acts as a conductor, ensuring these bursts fire off in a sequence dictated by the precise geometry of the system. The result is a cascading radio signal that moves through the frequencies in a pattern that directly mirrors the orbital periods and magnetic field strengths of the different stellar components. It's a natural engine, but one that uses the entire sextuple system as its parts, turning the architecture of the system itself into a giant celestial radio transmitter. This discovery didn't just solve a mystery. It unveiled an entirely new way for magnetic energy to be converted into radio waves on a scale and with a coordination we never knew was possible. This staggering level of synchronization is not a happy accident. It is the direct and inevitable result of a gravitational process known as tidal locking, taken to its most extreme possible conclusion. You're already familiar with a simple version of this phenomenon right here in our own solar system. Our moon is tidally locked to Earth, which is why we only ever see one side of it. Its rotation period, the time it takes to spin once on its axis, is exactly equal to its orbital period, the time it takes to circle Earth once. This lock was achieved over billions of years by Earth's gravity, creating a slight, elongated bulge on the moon. This bulge, in turn, experienced a gravitational tug that acted as a constant brake, slowing the moon's spin until it perfectly matched its orbit. In a simple two-body system like Earth and Moon, this is a fascinating detail. In a sextuple star system, this same basic principle is amplified into a symphony of interlocking rhythms. The process begins in the innermost, most violently intimate binary pairs. Here, the stars are so close that their gravitational pulls are titanic, distorting each other from perfect spheres into egg-shaped ovals. This tidal distortion creates immense internal friction, a force that acts as a powerful brake on their rotation. Very quickly, these stars surrender their independent spin, their rotation periods slowing until they exactly match their orbital periods. From that moment on, these two stars present the same face to each other for all eternity, locked in a permanent gravitational embrace. But this is just the first gear in a much larger machine. This newly synchronized inner pair now acts as a single, consolidated gravitational unit. Its combined mass and tidal influence then begins to work on the next binary pair in the hierarchical chain, slowly but surely breaking its rotation to match the broader orbital period of their dance around each other. This chain reaction of synchronization doesn't stop there. The now locked quadruple system exerts its own collective tidal force on the outermost, most distant binary pair. Though the gravitational pull is weaker across this vast distance, the timescales involved are immense, millions upon millions of years of relentless, gentle braking. Eventually, even this far-flung pair succumbs, its rotation falling into perfect step with its immensely long orbital period around the central four stars. The final result is a celestial clockwork of 6 individual stars, each spinning on its axis at a rate precisely determined by its position in the system's gravitational hierarchy. Their days, their years, and their rotations are all locked together in a precise, multi-layered mathematical ratio, a cosmic proof of the relentless and ordering power of gravity over deep time. The implications of this discovery reach far beyond mere orbital mechanics. It fundamentally alters the very environment within these systems. A tidally locked star is a profoundly different object from a freely spinning one. Because one hemisphere is permanently facing its companion, that side is subjected to constant, intense heating and gravitational stress. This can lead to extreme temperature differences between the star's day and night sides, potentially driving powerful supersonic winds that scream across its surface in a perpetual attempt to equalize the thermal imbalance. The star's magnetic field, which is generated by the churning of plasma in its interior, is also distorted and amplified by this forced synchronization, leading to the kinds of superflares and complex radio emissions we discussed earlier. The tidal locking doesn't just sync the motions, it engineers the stars themselves, creating conditions and active phenomena that simply cannot exist in isolation. Perhaps the most profound consequence of this cosmic synchronization is the unprecedented stability it grants the entire system. In gravitational dynamics, chaos is the default. The unpredictable interactions of multiple massive bodies usually lead to ejections or collisions on relatively short timescales, but a fully synchronized sextuple system has effectively found a way to eliminate the primary source of that chaos, independent rotation. By forcing every star's spin into a precise harmonic rhythm with every orbit, the system minimizes the transfer of energy and angular momentum between the orbits. It's the difference between trying to push a child on a swing randomly versus pushing them at the exact right moment in their arc. One method is inefficient and chaotic, the other builds a smooth, predictable, and stable rhythm. This synchronization acts as a gravitational gyroscope, dampening down perturbations and allowing this impossibly complex arrangement of 6 stars to endure, stable and harmonious, for time frames that dwarf the current age of the universe. This statistical improbability is one of the most compelling mysteries in all of astrophysics. If you were to sit down at a supercomputer and run a simulation of 6 stars forming from a single cloud, the outcome is almost always a cosmic catastrophe. The sheer gravitational bedlam, with every star pulling on every other star, introduces chaotic perturbations that amplify over time. The most common result is a violent gravitational slingshot, where one or more stars are flung out of the system at incredible speeds, destined to wander the interstellar void as rogue stars. The other frequent outcome is even more dramatic, a direct cataclysmic collision between 2 or more stars, an event that releases a staggering amount of energy and forges a new, bizarre stellar remnant. According to our best models, a random grouping of 6 stars should not be a stable, long-term configuration. It should be a fleeting, explosive event. Yet, the observational evidence is undeniable. We are not looking at young, freshly formed systems that are moments away from flying apart. We are looking at ancient stellar families, systems like our Cassiopeia or Castor itself, whose stars share chemical signatures indicating they have been bound together for billions of years. They have persisted for a significant fraction of the age of the universe, outlasting entire galactic epochs. This presents a glaring contradiction between theoretical prediction and observational reality, a paradox that forces astronomers to ask a profound question: what are we missing? How have these systems cheated the statistical odds for so long? The answer appears to lie in their very specific and non-random birth conditions. They are not the product of 6 random stars accidentally capturing each other. That scenario is as statistically likely as winning the cosmic lottery. Instead, the leading theory suggests they are born together, all siblings from the same dense core within a giant molecular cloud. This shared origin is the first critical ingredient for stability. As this core collapses, it doesn't fragment into 6 separate stars independently. It fragments in a hierarchical manner, first splitting into 2 or 3 smaller cores, each of which then fragments again into tight binary pairs. This means the stars are born with their delicate, resonant orbits already pre-programmed into the system from the very first moments of their existence. Their initial conditions are, by cosmic standards, incredibly fine-tuned. The system emerges with just the right amount of angular momentum, not so little that everything collapses inward, and not so much that the cloud flies apart before stars can form. The individual pairs are also born at those Goldilocks distances we discussed earlier, with orbital separations that are wide enough to avoid immediate merger but close enough to remain strongly bound. This precise arrangement allows the stabilizing mechanism of tidal locking to begin its work almost immediately, synchronizing the system's motions before chaotic perturbations can derail it. In essence, these ancient sextuple systems aren't the survivors of a chaotic battle royale. They are the carefully crafted products of a structured and surprisingly gentle birth process, endowed with a stability that has allowed them to weather the eons. They are not the rule, but the rare and magnificent exception that proves it. And amidst the gravitational turmoil and stellar transformations, we find yet another cosmic paradox, the birthplaces of planets themselves. In a calm, solitary system like our own, the story of planet formation is a gentle one. A vast, flat disk of gas and dust gracefully swirls around a young star, its material slowly coalescing into ever larger clumps that eventually become worlds. These protoplanetary disks are typically smooth, symmetrical rings, like a record spinning on a turntable, but transplant that same delicate process into the gravitational maelstrom of a young sextuple system, and the serene nursery becomes a celestial demolition derby. The discovery of these warped and shattered disks revealed a side of planet formation so violent and artistically chaotic it looks less like astronomy and more like a masterpiece of cosmic abstract art. The primary culprit is, unsurprisingly, the immense and competing gravitational pulls from the 6 stellar hosts. A smooth, coherent disk requires a single, dominant source of gravity at its center to maintain its orderly rotation. But in a sextuple system, there is no single center. Instead, the disk material feels a constantly shifting tug of war from multiple directions. The gravity from one star pulls one section of the disk outward, while the gravity from a different star, positioned at another angle, yanks a neighboring section in a completely different direction. The result is that the once orderly ring is sheared, twisted, and torn apart. It cannot maintain a flat plane. Instead, it gets warped into a complex three-dimensional shape, like a vinyl record that's been left in the sun too long. Some parts of the disk are pulled into tall, arching waves, while others are compressed into dense, narrow streams of material. This gravitational interference doesn't just warp the disk, it shatters it entirely. Instead of one continuous ring encircling the entire system, astronomers observe multiple fragmented disk segments, each one associated with a different star or binary pair. You might see a small, tight disk stubbornly clinging to the closest binary, while another, more distant disk fragment orbits a different pair. These are not complete rings, but arcs and clumps of dust, like islands of material isolated in a vast sea of empty space. The gravitational forces from the other stars act like cosmic shears, preventing the disk from ever forming a complete circle and stripping away vast swaths of planet-building material, either ejecting it into deep space or funneling it onto the stars themselves. The most stunning consequence of this gravitational sculpting is the emergence of structures within the disk that defy simple description. With advanced telescopes like the ALMA Observatory and the James Webb Space Telescope, we can now see these systems in incredible detail, and the images are breathtaking. We see not smooth rings, but intricate spiral arms of dust swirling out from the center like a galactic pinwheel. These are spiral density waves, permanently etched into the disk material by the rhythmic gravitational tugs of the orbiting stars. We see vast, dark gaps cleared out by the relentless pulling, and bright, concentrated knots of material where the dust has been gravitationally compressed. The overall effect is a swirling, ethereal sculpture of light and shadow, a constantly evolving work of art written in dust and gravity. Perhaps the most dramatic visual effect comes from the disk's warped geometry. Because the disk is not flat but bent and twisted, it casts long, complex shadows across itself and out into the surrounding nebula. As the stars and the disk components rotate, these shadows sweep and dance, creating a dynamic light show that changes in real time. From certain angles, a warped disk can eclipse one of the stars, causing a deep, asymmetric dimming that lasts for weeks. From other angles, the hidden star's light might shine over the top of the disk's curved edge, illuminating its upper layers and creating a brilliant halo effect. These shadow plays provide astronomers with a precise tool for mapping the disk's otherwise invisible three-dimensional structure, turning the system itself into a cosmic shadow puppet theater that reveals its own secrets. The sheer orbital velocity on display in some of these inner binaries is nothing short of breathtaking, pushing the very limits of what we thought was physically possible for a star. While our own planet plods along its orbit at a relatively leisurely 18.5 miles per second, the stars in these ultra-tight pairs are engaged in a frantic, relativistic sprint. We're talking about velocities that can reach several hundred miles per second, a significant fraction of the speed of light itself. To put that in perspective, a star in one of these systems could complete a full lap around Earth in less than a single second. This isn't just fast, it's a speed that exists on the very edge of known physics, a realm where the normal rules of stellar structure and material integrity should completely break down. These stars aren't just balls of gas, they are massive, complex structures held together by their own immense gravity. According to classical mechanics, an object spinning that fast should experience centrifugal forces so powerful that it would be ripped apart, its material flung out into space long before it could ever reach such incredible orbital speeds. The fact that we observe these stars not just surviving, but thriving at these velocities presents a fundamental puzzle. It's as if we discovered a ball of yarn spinning so fast it should unravel, yet it remains perfectly intact. This cosmic defiance forces us to reconsider the very nature of a star's tensile strength and the mysterious internal forces that allow it to withstand such extreme conditions. The secret to their survival appears to be a combination of their incredible density and their perfectly synchronized orbits. Many of these whirling dervishes are not giant, bloated stars. They are often compact, dense stellar remnants like white dwarfs or neutron stars, or incredibly tightly packed main sequence stars. Their high density means their gravity is overwhelmingly powerful, creating a gravitational bond so strong that it can counteract the tremendous centrifugal forces trying to tear them apart. Furthermore, because these pairs are almost always tidally locked, their rotation is perfectly smooth and balanced. There's no asymmetric flailing or uneven stress. They spin as a single, cohesive unit, distributing the insane forces evenly throughout their structures and preventing any single point from becoming a failure point. This discovery does more than just add another record-breaking fact to the astronomical books. It provides a unique natural laboratory for testing the limits of general relativity. At these velocities, the effects of Einstein's theory become pronounced and measurable. Time itself begins to slow down for these rapidly moving stars relative to the outside universe, an effect known as time dilation. Their orbits also exhibit a noticeable precession, meaning the point of their closest approach slowly rotates around over time, a phenomenon predicted by relativity that is dramatically amplified in such an extreme environment. By meticulously tracking these tiny deviations from Newtonian predictions, astronomers can conduct precision tests of relativity under conditions that are utterly impossible to recreate in any Earth-based laboratory. Perhaps the most astonishing implication is what these speed-limit-defying orbits tell us about the final fate of these systems. All orbiting bodies lose energy over time by emitting gravitational waves, and the amount of energy lost is incredibly sensitive to the orbital velocity. For these ultra-fast binaries, the energy loss is staggering. They are bleeding away orbital energy at a phenomenal rate, causing their orbits to shrink and their speeds to increase even further in a runaway feedback loop that can only end one way, in a spectacular, catastrophic merger. These stars are living on borrowed time, caught in a final, furious dance that will culminate in an event so energetic it will momentarily outshine entire galaxies. A fittingly dramatic end for a partnership that dared to dance at the edge of physics itself. The violence of these magnetic storms isn't confined to the space between the stars. It supercharges the stars' own atmospheres to levels of fury we can barely comprehend. We call the Sun's atmosphere the chromosphere and corona, a region that can erupt with solar flares. But in the quiet solitude of our solar system, these events are mere firecrackers compared to the astronomical fireworks display happening inside a sextuple system. Here, the constant gravitational grinding and magnetic field collisions don't just create occasional flares. They permanently push the stellar atmospheres into a state of hyperactive rage, creating chromospheres and coronae that are thousands of times more violent and energetic than our Sun's. This isn't a subtle increase in activity, it's a difference in kind, not just degree. Our Sun has an 11-year cycle where its flare activity rises and falls. A star in one of these complex systems has no such cycle. It exists in a permanent state of maximum eruption, a relentless storm with no calm eye. The mechanism behind this is a continuous and brutal process of magnetic braiding. The tidal forces from multiple companions keep the star's interior plasma in a constant state of churning turmoil, which in turn generates magnetic fields that are immensely strong and hopelessly tangled. These fields are constantly being stretched and wound up tighter by the star's rapid, synchronized rotation. It's like winding up a jack in the box millions of times without ever letting it pop, storing catastrophic amounts of energy that must eventually find a release. The result is a stellar flare so powerful it defies earthly analogy. A typical solar flare might release energy equivalent to millions of 100-megaton hydrogen bombs. A superflare from one of these locked stars can release thousands of times more energy than that in a single, apocalyptic burst. For a brief period, that one star can temporarily outshine the combined light of all 5 of its companions, making the entire 6-star system appear to double in brightness from our vantage point across interstellar space. These aren't just flashes, they are catastrophic explosions visible across the galaxy, pumping out not just visible light but a deadly flood of X-rays and ultraviolet radiation that scours every corner of the system. The most incredible aspect of this phenomenon is that we can actually map this activity from light years away. Astronomers use a technique called spectrophotometry to isolate the light coming specifically from the chromosphere of a star. They look for the telltale emission lines of calcium and hydrogen, which act like a thermometer for stellar violence. In a normal star, these lines are relatively faint. In these systems, these spectral lines are not just bright, they are monstrously overactive, indicating a chromosphere that is not a placid layer of gas but a continuous, roiling sea of plasma ejections and magnetic reconnection events. It's a direct measurement of a star that is quite literally boiling over with pent-up energy, its surface a perpetual battlefield of forces unleashed by its chaotic family life. Perhaps the most unsettling discovery is that these majestic cosmic clocks, which we assumed ticked with the glacial precision of deep time, are actually changing right before our eyes. For centuries, astronomy has been the study of a seemingly permanent and predictable heavens, where orbital periods are measured in millennia and any visible change requires generations of patient observation. But when astronomers began meticulously timing the eclipses in systems like V905 Scorpii, they were met with a profound shock. The intricate dance of these 6 stars is not fixed, it is actively evolving. The orbital periods of the inner binaries are measurably shrinking or expanding over the course of just a few decades, a timescale so brief it's the astronomical equivalent of watching a mountain range visibly rise and fall within a single human lifetime. This shouldn't be happening. According to our most robust gravitational models, the orbits in such a complex but hierarchical system should be remarkably stable over these short timescales. The primary mechanism for orbital change is the loss of energy through gravitational waves, but that process is incredibly slow and gradual for all but the most extreme, ultra-tight binaries. The changes we're seeing are far too rapid to be explained by that alone. It's as if we discovered a perfectly engineered grandfather clock that, instead of ticking consistently, suddenly speeds up or slows down by a few seconds each day for reasons completely hidden inside its mechanism. This anomaly suggests there are powerful forces at work within these systems that our current physics is simply not accounting for, a hidden engine driving an evolution we can barely perceive. One compelling hypothesis points to the stars themselves not as static spheres, but as dynamic, fluid bodies. Many of these stars are not perfect spheres. They are tidally distorted into egg shapes, and this distortion travels around the star as it orbits, creating a perpetual wave on its surface. This process consumes a tiny amount of orbital energy, slowly breaking the system, but a more dramatic effect may come from magnetic braking. These stars are often rapid rotators with immensely powerful magnetic fields. A magnetic field acts like an anchor dragging through the tenuous outer layers of the star's atmosphere, the corona. This creates a constant, subtle friction that saps angular momentum from the star's rotation. In a tightly bound binary, the star's spin is directly coupled to its orbit through tides, so breaking the star's rotation also breaks the orbit itself, causing the two stars to spiral imperceptibly closer together over time. Another fascinating possibility involves a hidden third body within an already complex dance. While we observe 6 stars, there could be additional, unseen actors in this play, substellar objects like brown dwarfs or even Jupiter-sized planets on wide, perturbing orbits. The gravitational tug from such a body, as it swings through its long path, could periodically pull on the inner binaries, subtly transferring energy and angular momentum, and causing their orbits to wobble and their periods to oscillate in a long-term cycle. We would only be seeing a small segment of that cycle, making it look like a permanent and mysterious trend. The most exotic explanation, however, ventures into the realm of orbital resonance. We know resonances stabilize these systems, but they can also drive instability. If the orbital period of one binary pair is in a precise resonant ratio with the precession rate of another pair's orbit, it can create a feedback loop. Energy can be pumped from one orbit to another, causing one pair to tighten while the other expands, all while the total energy of the system remains conserved. This would mean the system isn't decaying or losing energy. It's simply redistributing it internally in a complex, long-term cycle we are only now beginning to witness. The changes we measure over decades might be just one small phase of a millennia-long orbital breathing motion, a rhythm of contraction and expansion on a scale we've never before had the precision to detect. This isn't a sign of impending doom, but rather a glimpse into the living, breathing dynamics of a truly complex gravitational organism. And perhaps nowhere is the defiance of conventional wisdom more apparent than in the strange and mismatched binary pairs found at the heart of some of these systems. You might expect that 6 stars born together would be a relatively uniform family, siblings that share a common age and a similar chemical heritage. Yet, when astronomers perform a detailed census of the individual members, they sometimes find pairs locked in a tight orbital embrace that are, for all intents and purposes, complete strangers. These are stellar odd couples, partnerships so bizarre they seem to break the fundamental rules of star formation, suggesting a history far more complex and violent than a simple, shared birth. Consider a hypothetical but scientifically plausible pair, a massive, brilliant blue O-type star, a behemoth that lives fast and dies young, bound inextricably to a tiny, cool, ancient red dwarf. On the face of it, this pairing makes no sense. These 2 stars are from completely different stellar generations and social classes. The O star, with a mass dozens of times that of our Sun, has a lifetime measured in mere millions of years. It is a cosmic infant. The red dwarf, by contrast, is the ultimate stellar miser, burning its hydrogen fuel so slowly that it can shine for trillions of years, far longer than the current age of the universe. It is effectively immortal. For these two to be found as a close binary pair, they must have formed at nearly the same time from the same cloud of gas. But that would mean the red dwarf has been around since the beginning, while its massive partner should have exploded as a supernova eons ago. Their very existence together is a chronological impossibility. The solution to this paradox is as dramatic as it is unexpected: stellar theft on an interstellar scale. The prevailing theory suggests that these mismatched pairs are not siblings at all, but rather celestial orphans adopted from different families. The sextuple system, with its complex gravitational field, acts like a cosmic fishing net. As it moves through its native star cluster or the galactic disk, it can gravitationally capture lone stars or even break apart weaker binary systems that wander too close. This process, called dynamical capture, would have been most effective when the system was young and still embedded in its dense natal cluster, a crowded stellar nursery where close encounters were common. Imagine the scene. A young, unstable triple star system drifts too close to the forming sextuple system. The gravitational pull from the sextuple's massive members acts like a tidal force, stretching and distorting the passing triple. In the ensuing chaos, one star from the triple might be ejected at high speed, while another is captured into a new orbit around one of the sextuple stars. The captured star, with its own unique age and chemical signature, is now permanently bound to a family it was not born into. This would explain the impossible age gaps and the strange chemical differences between stellar partners. We are not looking at a unified family, but a blended one, a gravitational mosaic built from the pieces of different stellar dynasties. This capture theory provides the most elegant explanation for another class of strange binary, the chemically peculiar pair. Spectroscopy reveals that some partners have surface abundances of elements like mercury, manganese, or europium that are thousands of times higher than in their binary companions. These elements are not produced in the same types of stars. Their overabundance is the result of very specific and rare nuclear processes. For two stars that supposedly formed from the same well-mixed cloud of gas to have such radically different surface chemistries is virtually impossible. But if one star was captured from a different region of the galaxy, perhaps from a cloud that had been enriched by the supernova of a very specific type of star, then its strange chemical signature is a permanent record of its original hometown, a cosmic passport stamp it will never lose. The implications of this are profound, forcing a rethink of how we define a star system. We can no longer assume that all stars in a gravitationally bound group are genetically related. A sextuple system may not be a single family, but a gravitational empire, its members acquired through conquest and alliance over millions of years. This makes each one a unique archaeological site. By studying the properties of these captured stars, we can learn about the conditions in other parts of the galaxy, or even in other star clusters that have long since dissolved. These strange binary pairs are more than just orbital curiosities. They are living records of the dynamic and often violent gravitational interactions that shape our galaxy. This constant gravitational intimacy gives rise to one of the most visually spectacular and physically transformative processes in all of astronomy: the direct exchange of stellar material between companions. In a solitary star, evolution is a lonely, inward journey, a slow and private burning of its own fuel until it can no longer sustain the reaction. But in the tight binary pairs at the heart of a sextuple system, stellar evolution becomes a collaborative and often violent group project. Stars so close together don't just influence each other with their gravity. They can literally reach out and steal the very substance of their partners, turning the space between them into a rushing river of superheated gas. This process, known as mass transfer or Roche-Lobe overflow, begins when one star in a tightly bound pair ages slightly faster than its companion. As it exhausts the hydrogen in its core, it begins to expand, evolving into a red giant or subgiant. In isolation, this expansion would simply continue unimpeded. But in this crowded stellar apartment, the expanding star's outer atmosphere quickly reaches the boundary of its gravitational territory, a teardrop-shaped region of space called its Roche lobe. This invisible bubble defines the space where its own gravity is stronger than the pull of its companion. The moment its atmosphere balloons beyond this limit, the balance of power shifts. The companion star's gravity suddenly becomes the dominant force on that spilled material, and it begins to siphon it away. What happens next is a breathtaking cosmic spectacle. This siphoned gas doesn't simply fall directly onto the other star. Because the entire system is rotating rapidly, the stolen material conserves its angular momentum, causing it to spiral inward in a vast, whirling disk known as an accretion disk. This disk orbits the receiving star like a miniature version of Saturn's rings, glowing with an intense, white-hot fury from the incredible friction and compression within it. The inner regions of this disk can reach temperatures of millions of degrees, making it a prodigious source of X-ray radiation, a telltale sign of active mass transfer that astronomers can detect across interstellar distances. The consequences for both stars involved are nothing short of revolutionary. For the donor star, this process is a form of cosmic surgery, abruptly halting its normal evolution. It's stripped down to its hot, dense core long before its natural lifespan is over, prematurely transforming it into a stellar remnant like a helium-white dwarf. For the receiving star, it's like winning the galactic lottery. It gains a massive, sudden infusion of fresh hydrogen fuel, which rains down onto its surface and is churned into its core by the tumultuous energy of the impact. This new fuel reignites its nuclear fusion with a vengeance, causing it to become hotter, bluer, and more luminous than any star of its original mass has any right to be. It is effectively rejuvenated, its evolutionary clock reset to zero, making it appear billions of years younger than its plundered sibling. This incredible cycle of theft and renewal doesn't just change the stars, it alters the entire system's dynamics. The transfer of mass represents a transfer of momentum. As the donor star loses mass, its gravitational grip on its companion weakens, causing their orbital separation to increase. Conversely, if the accretion disk somehow becomes unstable and ejects material from the system entirely, the loss of mass can cause the binary pair to spiral closer together. This constant, subtle tweaking of the orbits can have ripple effects throughout the entire sextuple hierarchy, potentially nudging other binary pairs into new resonances or altering the timing of their eclipses. The act of one star feeding on another becomes an engine for orbital change, proving that in a gravitationally complex system, nothing happens in isolation. Now consider the ultimate navigational challenge, a puzzle that makes plotting a course through our simple solar system look like child's play. The intricate gravitational dance of a sextuple star system doesn't just create a beautiful light show. It weaves a labyrinth of moving gravity wells, a constantly shifting maze of forces that would render any conventional star chart utterly useless within moments. A spacecraft attempting to traverse this environment wouldn't be sailing on a static sea of stars. It would be trying to navigate a cosmic whirlpool where the currents change direction every second, and the safe channels are in a state of perpetual, unpredictable flux. The problem stems from the fact that you're not dealing with one or even two dominant sources of gravity. You have 6 massive objects, all moving in different directions at different speeds, each exerting its own pull on your vessel. Their combined gravitational field isn't a simple, smooth landscape with hills and valleys. It's a chaotic, churning ocean of forces that amplify and cancel each other out in rapidly changing patterns. Within this maelstrom, there exist regions of temporary stability known as Lagrange points, cosmic eddies where the gravitational and centrifugal forces briefly balance. But in a sextuple system, these points are not fixed in space. They race along incredibly complex paths, appearing, vanishing, and reappearing elsewhere in a matter of hours or days as the stars complete their frenetic orbits. A safe harbor you chart one day could be in the heart of a gravitational tsunami the next. This turns navigation from a problem of calculation into one of real-time prediction on an unimaginable scale. A ship's computer couldn't rely on a pre-plotted course. It would need to continuously solve the full, nightmarish six-body problem in real time, factoring in the precise mass, velocity, and position of every single star, and then calculating the evolving location of these fleeting stable zones. The computational power required is staggering, far beyond even our most advanced supercomputers, because you're not solving it once. You're solving it millions of times per second to account for the infinitesimal changes in trajectory that occur with every passing moment. A single processing delay or a rounding error in the 11th decimal place could compound into a catastrophic course deviation, sending the ship spiraling into a deadly gravitational slingshot or on a collision course with a star. The sheer number of variables involved introduces a level of complexity that borders on the philosophical. To plot a truly safe course, the navigation system would theoretically need to account for everything, from the subtle gravitational influence of Jupiter-sized planets within the system to the minute loss of mass from the star's stellar winds, and even the tiny but cumulative push of radiation pressure from each of the 6 suns. It's a system so sensitive to initial conditions that it exemplifies chaos theory. The metaphorical flutter of a butterfly's wing in the form of a tiny sensor miscalibration could utterly change the predicted outcome days or weeks down the line. This isn't just a maze, it's a maze whose walls are made of flowing water and whose floor is made of shifting sand, a puzzle designed by nature that seems almost purpose-built to defy solution. The very act of traversal would be a high-stakes dance, a continuous series of minute corrections where the price of a misstep is not a wrong turn but oblivion. In the quest to classify every flicker in the night sky, astronomers have created an entire taxonomy of variable stars, each with its own predictable pattern. There are Cepheids which pulse with a steady rhythm and eclipsing binaries which dim and brighten like a perfect metronome. But when they turned their telescopes toward the heart of these sextuple systems, that entire orderly catalogue was thrown into disarray. The light curves they recorded didn't just defy classification. They seemed to mock the very idea of it, displaying patterns of such baroque complexity that they were initially mistaken for signals from multiple, entirely new classes of stellar objects happening to occupy the same point in space. The root of this confusion lies in the sheer number of overlapping cycles. Imagine trying to listen to an orchestra where every single instrument is playing a different song, but all at the same time. In a sextuple system, you have not one, but 3 separate clocks ticking at once. The innermost, ultra-tight binary pair might be whirling around each other every few hours, creating a rapid, staccato series of eclipses. The next binary pair out could have an orbital period of several weeks, adding a slower, deeper rhythm to the mix. And finally, the wide outer binary, with its orbit stretching across centuries, imposes a grand, glacial trend on top of it all. The final light curve is a superposition of all these rhythms, a stellar symphony where the notes from 3 different movements are being played simultaneously. This creates bizarre and beautiful patterns that initially look like random noise. You might see a series of deep, sharp dips from the close binaries' eclipses, but these are superimposed on a broad, shallow wave from the intermediate pair's orbit. Then, over years of observation, you might notice that the entire pattern is itself slowly getting brighter or fainter as the orientation of the widest pair changes, altering the total amount of light we receive from the entire family. The result is a light curve with patterns that repeat, but never in exactly the same way. A dip might be deep one time and shallow the next because it coincided with the brightening phase of a slower cycle. It's a chaotic, yet strangely harmonic, interplay of light and shadow. The initial confusion among astronomers was profound. A light curve from one of these systems might show a primary dip that looks exactly like a standard eclipsing binary, but then it would be followed by a series of secondary dips that didn't match any known model. Some systems were even catalogued multiple times under different variable star designations because different sections of their decades-long light curve suggested completely different behaviors. It was only through patient, long-term monitoring and the application of immensely powerful computer algorithms that researchers could finally disentangle the individual melodies from the cosmic cacophony, identifying the specific orbital periods of each contributing pair and revealing the true hierarchical nature of the beast. This discovery did more than just solve a puzzle. It unveiled a new physical phenomenon. In some systems, the light curves revealed changes that couldn't be explained by simple eclipses. Astronomers observed subtle, asymmetrical brightening before and after a primary eclipse, or an overall change in the system's baseline brightness between orbital cycles. These were the signatures of intense tidal heating. The gravitational forces at play are so powerful that they literally stretch and compress the stars themselves, heating their interiors through friction, much like Jupiter's gravity flexes and warms its moon Io. This internal heating can cause a star to glow brighter outside of its normal nuclear burning, adding yet another layer of variation to an already impossibly complex light signature. The star isn't just being hidden, it's being physically altered by the dance, its very luminosity becoming a direct readout of the gravitational forces acting upon it. Think of the galaxy as a vast, churning ocean where stars are born, live, and die in a continuous cycle of creation and destruction. Over billions of years, the gentle gravitational tides of passing star clusters and the immense shockwaves from nearby supernova act like cosmic erosion, slowly pulling apart binary and triple star systems, scattering their members to the interstellar winds. It's a hostile environment for any delicate gravitational arrangement, which is why finding a truly ancient system is exceptionally rare. Yet, against all odds, the most complex systems of all, these intricate sextuplets have not only survived but have done so with their original architecture almost perfectly intact. They aren't just old, they are cosmic time capsules, pristine relics from a much earlier era in the universe's history, sealed shut by the very complexity of their own gravitational bonds. Their incredible longevity is their most valuable feature. While a simple binary pair can be easily disrupted by a close encounter with another star, a sextuple system is a gravitational fortress. The hierarchical structure, with its distinct layers of tight inner binaries and wide outer orbits, creates a profound stability. A passing star might give the outermost binary pair a gentle gravitational nudge, but that perturbation is distributed and diluted as it travels inward through the system's layers. By the time its influence reaches the frantic inner binaries, the effect is minuscule, a tiny ripple that does nothing to disrupt their synchronized dance. This layered defense mechanism makes them incredibly resilient to the external chaos of the galaxy, allowing them to persist for billions of years virtually unchanged, preserving a record of the conditions in which they were born. This opens up an astonishing possibility. By studying the precise orbital parameters and chemical compositions of these systems, we might be able to peer back in time to the early galaxy. Their current state is a living fossil, a snapshot of a specific moment in cosmic history. For instance, the exact ratios of certain heavy elements within their stars could tell us about the specific supernova explosions that seeded the giant molecular cloud from which they collapsed. A system born from a cloud enriched by a particular type of supernova, one that produced an unusual amount of europium or gold, for example, would carry that unique chemical signature forever, a permanent record of a stellar death that occurred over 10 billion years ago. Furthermore, their very existence and specific configuration could tell us about the density and temperature of the early galactic environment. A sextuple system requires an incredibly dense, cold, and massive cloud of gas to form through hierarchical fragmentation. By measuring the masses and separations of the stars today, astronomers can work backward, running sophisticated simulations to determine the precise initial conditions that could have given rise to such a system. It's like finding a perfectly preserved prehistoric insect in amber. By studying its every detail, we can reconstruct the entire ecosystem it lived in, an ecosystem that has long since vanished. These systems are not just collections of stars, they are celestial archives holding data about the infant Milky Way that we cannot access through any other means, offering a direct window into a time when the universe was young and the galaxy was a very different place. But the surprises within these stellar families aren't limited to the light our eyes can see. Some of the most astonishing discoveries were made by tuning into the universe's most energetic channels. For decades, astronomers had catalogued the various types of stars within these sextuple systems, a mix of main sequence stars, giants, and dwarfs. Based on everything we knew, none of these stars individually should have been capable of producing a significant amount of high-energy X-ray radiation. That kind of emission is typically reserved for the most extreme objects in the cosmos, the remnants of dead stars like neutron stars or black holes actively feeding on a companion. So when X-ray observatories like Chandra and XMM Newton turned their gaze toward these systems and detected a veritable firestorm of high-energy X-rays, the data initially seemed to make no sense at all. It was like pointing a thermal camera at a group of people and finding one of them was radiating the heat of a blast furnace. The intensity of the signal was the first major clue that something extraordinary was happening. This wasn't just a faint X-ray glow, it was a powerful, persistent torrent of energy that in some cases outshone the combined visible light of all 6 stars. The immediate assumption was that they had stumbled upon a hidden stellar corpse, a neutron star or black hole that had somehow escaped detection amidst the brilliant glare of its 6 siblings. But careful analysis ruled this out. The X-ray emission wasn't coming from a single, compact point. Instead, it seemed to be diffuse, emanating from the vast spaces between the stars themselves, particularly from the regions where the powerful stellar winds from different stars were on a direct collision course. This revelation unlocked the true, violent mechanism at work. Each of these stars, especially the hotter, more massive ones, blows off a continuous stream of charged particles, a stellar wind. In a single star system, this wind expands outwards relatively unimpeded. But in the cramped, chaotic quarters of a sextuple system, these winds don't get far before they slam into each other at phenomenal speeds. Imagine 6 hurricane-force winds, each emanating from a different star, all meeting in the center of the system. When these supersonic plasma streams collide, they don't just gently mix, they create immense, standing shock waves in the space between the stars, cosmic sonic booms frozen in place by the relentless pressure from all sides. It is within these permanent shock fronts that the real particle acceleration magic happens. The chaotic magnetic fields churned up by the colliding winds act as a natural and incredibly powerful particle accelerator, far more effective than anything we could ever build on Earth. Charged particles, electrons and protons, get caught in these magnetic maelstroms and are whipped back and forth across the shock front, gaining a tremendous amount of energy with each pass. When these ultra-relativistic particles finally escape or spiral along magnetic field lines, they release their pent-up energy in the form of high-energy X-rays. This process transforms the entire central volume of the sextuple system into a giant, natural particle collider, generating X-rays on a scale and of a luminosity that astronomers had never before associated with multiple star systems. The system itself becomes the engine, using the collective energy of its stars' winds to power a radiation source that none of its members could produce alone. But the grand architecture of these systems extends its influence far beyond their own stellar members, warping the very fabric of space around them to create one of the most visually surreal phenomena in all of astronomy. Einstein's theory of general relativity tells us that mass bends spacetime, and anything traveling through that warped space, including light, must follow a curved path. We see this in dramatic fashion when a massive galaxy cluster acts as a gravitational lens, bending the light from a more distant galaxy into a brilliant arc or even a complete ring known as an Einstein ring. Now imagine that same principle applied not to a single monolithic galaxy, but to 6 individual stars in complex motion. The combined mass of a sextuple system is more than enough to create its own lensing effect, but the result is not a single stable ring. It is a dynamic, ever-shifting funhouse mirror of light, a natural cosmic kaleidoscope that constantly reconfigures itself. The lensing effect here is profoundly different from the static distortion caused by a large, distant galaxy. Because the stars are all moving, the landscape of their combined gravitational field is in a state of perpetual flux. As the stars whirl around in their orbits, their individual gravity wells move with them, creating a constantly evolving pattern of peaks and valleys in the fabric of spacetime. A distant background star whose light is traveling through this chaotic region on its way to our telescopes doesn't experience a single, smooth bend. Instead, its light rays are tugged and pulled by each passing star in the system, following a path that changes from week to week, day to day, even hour to hour. From our perspective, this makes the background star appear to dance and flicker in the sky, its position wobbling and its brightness amplifying and fading in a complex rhythm dictated by the orbital motions of the 6 foreground stars. This creates a spectacular opportunity for what astronomers call multi-messenger astronomy. By meticulously tracking the intricate dance of a lensed background star, they can achieve 2 groundbreaking measurements at once. First, the precise pattern of the light's wobble and brightening acts as a direct probe of the gravitational field of the sextuple system itself. It's like using the distant star's light as a tracer die to map the invisible contours of the gravity wells as they move. This provides an incredibly precise way to measure the masses of the individual stars in the system, a detail that is often difficult to pin down with other methods. The lensing effect doesn't lie. The degree to which the light is bent directly reveals the mass of the object doing the bending, offering an independent and highly accurate check on our other estimates. Simultaneously, this natural lens acts as a magnificent magnifying glass. During the precise moments when one of the stars in the system passes directly between us and the background star, the gravitational lensing effect can amplify the distant star's light by a factor of hundreds or even thousands. This temporary brightening, known as microlensing, allows us to study that background object in exquisite detail that would otherwise be utterly impossible. We might be able to resolve surface features on a star in a different galaxy, or detect the subtle dimming caused by planets orbiting it, all thanks to the precise alignment and immense gravity of this intervening stellar family. A single sextuple system can thus become a natural observatory, its gravitational power granting us a fleeting but incredibly detailed view across truly cosmic distances. The most fascinating aspect is the predictive challenge this presents. To untangle the lensing signal, astronomers must create a dynamic model of the entire system's mass and motion, and then calculate how that specific arrangement will distort the path of light from every possible angle. It is a computational feat of staggering complexity, a real-world test of our ability to model general relativity in an environment of incredible dynamism. Successfully predicting the exact timing and pattern of these microlensing events is one of the strongest validations of both our orbital models for these systems and Einstein's theory itself. We are not just passive observers of this cosmic kaleidoscope. We are learning to read its patterns, using the distorted light of distant suns to illuminate the darkest secrets of the 6 closest to us. This cosmic resilience brings us to one of the most hotly debated mysteries surrounding these systems. How did they form in the first place? the very existence of a stable sextuple star system seems to fly in the face of probability, presenting a paradox that has led astronomers to propose some truly wild and competing theories. The central question is profound. Did these 6 stars all form together as one big, happy family? Or is what we see today the result of a series of incredible celestial kidnappings, a gravitational empire built over eons through capture and conquest? The traditional and most widely accepted theory is known as monolithic collapse or core fragmentation. This is the idea that all 6 stars are true siblings, born from the same incredibly dense, massive, and turbulent core within a giant molecular cloud. In this scenario, the system's complex hierarchy is baked in from the very beginning. As the massive cloud core begins to collapse under its own gravity, it doesn't simply contract into a single point. Instead, the initial turbulence and rotation cause it to fragment, not into 6 individual stars chaotically, but in an orderly, nested fashion. It might first split into 3 smaller, spinning clumps of gas. Each of these clumps then undergoes its own gravitational collapse, fragmenting a second time to form a tight binary pair. This process imprints the precise, resonant orbits and perfect balance needed for long-term stability directly into the system's DNA, like a cosmic recipe followed with impeccable precision. However, there's a competing theory that is far more dramatic and to many seems almost too fantastical to be true: the dynamic capture model. This idea suggests that the current system is not a single family but a blended one, a gravitational amalgamation of stars from different origins. Imagine a young, unstable triple star system drifting through a densely packed star cluster. By pure chance, it wanders too close to another triple system. The gravitational forces between them become immense, pulling and twisting their orbits into a chaotic dance. In the ensuing gravitational turmoil, 1 or 2 stars might be violently ejected into interstellar space, while the remaining 4 or 5 stars settle into a new, stable configuration. Over millions of years, this new, larger system might then encounter another lone star or binary pair, capturing it too in a delicate maneuver that requires just the right amount of energy to be lost from the system to make the new member stick. This would make a sextuple system not a birthright, but a prize won through a series of unlikely cosmic encounters. The statistical improbability of the capture theory is what makes it so compelling and so contentious. For a capture event to be successful, the encounter must be close enough for a strong gravitational interaction, but not so violent that it destroys the systems involved or flings all the stars away. Furthermore, the interaction must occur in just the right way for the system to lose enough kinetic energy through friction, gravitational waves, or the ejection of other stars, to allow the new member to become bound rather than just whizzing past on a hyperbolic orbit. To have this happen not once but multiple times, building a system of 6 stars, is a level of cosmic serendipity that is staggeringly rare. It would be like throwing a handful of marbles into the air over and over again and having them, against all odds, eventually land perfectly stacked in a pyramid. Proponents of this theory argue that while the odds for any one system are infinitesimally small, the vastness of the galaxy and the billions of years available make it a possibility we cannot ignore. The most intriguing evidence for this capture theory comes from the strange stellar odd couples we find within some of these systems. If all 6 stars are siblings, they should share a common age and a similar chemical composition, having all formed from the same well-mixed cloud of gas. Yet, spectroscopic analysis sometimes reveals glaring mismatches. You might find a hot, massive, and therefore short-lived star locked in a tight orbit with a cool, ancient red dwarf that should be its senior by billions of years. Their very existence together is a chronological impossibility unless they originated in different stellar nurseries. The chemical fingerprints can be even more telling. One star might have a surface rich in rare elements like europium or mercury, a signature of a very specific type of supernova explosion that polluted its birth cloud, while its immediate binary partner shows a completely normal, solar-like abundance. This is the strongest possible evidence for capture. These stars are carrying the unique passports of their original homes, proving they were not born into the family they now call their own. Ultimately, the truth may lie in a hybrid of these two models. Perhaps the core of the system, a stable quadruple arrangement formed through monolithic collapse, its resonant orbits providing a sturdy gravitational anchor. Then, later in its life, as it moved through its native star cluster, this quadruple system acted as a massive fishing net, gravitationally capturing one or two additional binary pairs that wandered too close. This would explain both the incredible fine-tuning of the inner orbits and the presence of any chemical or age mismatches in the outer stellar pairs. This combined theory paints a picture of a universe that is both structured and dynamic, where systems can be born with order but can also grow and evolve through violent and unpredictable encounters, creating the magnificent and improbable cosmic architectures we are only just beginning to understand. Perhaps the most elegant discovery within these complex systems is one that appeals to our innate love of pattern and harmony, the realization that the orbital periods of these stellar pairs are not random, but locked together in precise mathematical ratios. This is the phenomenon of orbital resonance, and finding it in a sextuple system is like discovering that a chaotic, free-form jazz improvisation has been secretly following a complex yet perfect symphony score all along. These aren't just stars moving in space, they are a celestial orchestra, with each binary pair playing its note at an interval that creates a chord of gravitational stability. These resonances appear as ratios of small integers. For instance, the innermost binary might complete exactly 3 orbits in the precise time it takes the next binary out to complete 2 orbits, a 3-2 resonance. The wider pair might then complete 1 orbit for every 5 orbits of the intermediate pair, a 1-5 ratio. These are not coincidences. They are the fundamental mechanism that allows such a complex system to remain stable over astronomical timescales. The resonances act as a gravitational metronome, synchronizing the motions of the stars so that their gravitational tugs always reinforce the system's structure rather than tearing it apart. It ensures that when one pair is at its closest, most gravitationally influential point, the other pairs are in positions that minimize chaos, their pulls canceling out disruptive effects. This self-tuning is a dynamic process. Astronomers believe these systems aren't born with these perfect ratios already in place. Instead, they emerge over millions of years through a relentless process of gravitational friction and energy dissipation. Imagine a slightly out-of-tune guitar string. When you pluck it, the vibration is unstable and produces a dissonant sound, but through subtle adjustments tightening the peg ever so slightly, the string finds its true pitch and rings clear. In a sextuple system, gravity acts as the hand on the tuning peg. The gravitational interactions between the pairs are constant and unforgiving. Orbits that are even slightly askew experience stronger tidal forces, which sap energy and gradually alter their periods. This slow, relentless process continues until the orbits inevitably snap into a resonant configuration, a state that minimizes the energy loss and maximizes stability. The system, in essence, tunes itself, finding the one harmonious arrangement that allows its incredible complexity to endure. And here's where the mystery deepens into a full-blown cosmic paradox. If you were to ask any astrophysicist where a delicate, complex structure like a sextuple star system would be most likely to die, the answer would be immediate and unanimous: in a dense star cluster. These crowded stellar cities are the most violent gravitational environments in the galaxy, where close encounters between stars are common and the tidal forces are strong enough to rip apart binary pairs or fling stars into the void. It's the last place you'd expect to find such a fragile, intricate arrangement of 6 gravitationally bound stars, yet that's exactly where we keep finding them. It's like discovering a house of cards standing perfectly intact in the middle of a hurricane. It defies all logic and points to a hidden source of resilience we are only just beginning to understand. This survival isn't just a matter of luck, it's a testament to an ingenious architectural design. The very complexity that makes these systems seem so fragile is actually the source of their incredible strength. Think of it like this: a simple binary system is a seesaw with two people. A passing star can easily disrupt their balance, giving one a gravitational push that sends the other flying. But a hierarchical sextuple system is more like a gyroscope, a complex, spinning wheel within a wheel. When an external force tries to push it, the internal motions absorb and redistribute the energy. A gravitational nudge from a passing star might give the outermost binary pair a slight shove, but that perturbation has to travel inward through the system's layers. By the time it reaches the ultra-tight inner binaries, the disruptive energy has been spread out and diluted by the complex interplay of all the other orbits. The inner dancers remain perfectly synchronized, completely unaware of the chaos that just passed by outside. This inherent stability turns them into the ultimate cosmic survivors, the old-growth sequoias of the star cluster. While simpler binary and triple systems are constantly being broken apart by close encounters, the sextuple systems persist. They act like gravitational anchors, their collective mass making them far harder to disrupt. In fact, they might even be the predators in this environment, not the prey. A passing single star or a weaker binary system that gets too close can itself be torn apart by the sextuple's powerful gravity. The six-star system can capture the intruder, ejecting one of its stars while absorbing the other, growing even more massive and stable in the process. They aren't just surviving the chaos of the cluster, they are mastering it, using the relentless gravitational interactions to their advantage in a way that simpler systems simply cannot. This incredible longevity makes them invaluable time capsules. A dense star cluster is a dynamic environment. Stars are constantly being ejected, and the cluster itself slowly dissolves over billions of years. The fact that a sextuple system has survived there since the cluster's formation means it contains a pristine record of the cluster's initial conditions, its original mass, density, and chemical composition. By studying these ancient stellar families, we aren't just learning about the systems themselves, we are peering back in time to the birth of the entire cluster. They are living fossils, preserving a chapter of galactic history that would otherwise be lost forever. A chapter written in the complex, harmonious motion of six stars that have weathered the storm together since the dawn of time. But the grandest challenge of all lies not in observing the dance, but in decoding its music, the starlight itself. When astronomers first turned their spectroscopes toward these systems, they expected a complex but ultimately solvable puzzle. Instead, they were met with a spectroscopic nightmare, a chaotic jumble of shifting lines that defied all initial attempts at interpretation. The spectral lines, those unique barcodes that reveal a star's chemical composition and motion, weren't just shifting back and forth in a predictable rhythm. They were blurring, splitting, and weaving across the spectrum in patterns so bizarre they appeared to violate the very laws of physics. The heart of the problem lies in the sheer number of overlapping Doppler shifts. A single star moving toward us has its light blue-shifted. A star moving away is red-shifted. In a sextuple system, you don't have one or two sources of motion. You have six stars all moving in different directions at different speeds, each imprinting its own unique Doppler shift onto the collective light. From our distant vantage point, the light from all six stars is blended into a single beam. The spectrometer doesn't see six individual stars, it sees one incredibly confused source of light, its spectral lines stretched and compressed by multiple competing forces simultaneously. A single absorption line for calcium, sharp and distinct in a solitary star, becomes a broad, smeared-out band, as if someone had dragged a wet brush across the spectrum. The most baffling early observations were of spectral lines that seemed to behave in ways that were downright impossible. Astronomers would track a specific line, only to see it split into two distinct components that would move apart, then cross over each other, then merge back into one, only to split again moments later. Some lines would appear to stutter, blinking in and out of existence at different phases of the orbital cycle. Others would change their depth and shape, becoming strong and deep at one moment and then almost vanishing the next. This wasn't just complex, it was a form of cosmic sleight of hand, a spectroscopic illusion that made it seem like elements were appearing, disappearing, and moving at impossible speeds. Untangling this mess required a shift in thinking as dramatic as the discovery of the systems themselves. Astronomers realized they couldn't approach the data as a single spectrum. They had to treat it as a complex cryptographic signal, a cipher with 6 independent keys moving in 3 different orbital planes. The breakthrough came from applying powerful computer algorithms capable of running millions of simulations, each one testing a different possible configuration of masses and orbits. The computer would generate a predicted composite spectrum for a hypothetical system, then compare it pixel by pixel to the observed data. Slowly, through this relentless process of elimination, the ghostly fingerprints of the individual stars began to emerge from the noise. The reward for this decades-long effort was a treasure trove of information. By finally isolating the spectral lines of each component star, astronomers could not only confirm their orbital motions but also measure their masses, temperatures, and chemical compositions with stunning precision. That strange dancing of the spectral lines wasn't an error. It was a direct recording of the stars whipping around their orbits, their light being stretched and squeezed by their immense velocities. The moments when lines blurred into a continuous smear corresponded to times when 2 stars were moving across our line of sight at their highest speeds, while the moments of clarity occurred when their motion was primarily toward or away from us. The spectrum itself had become a precise clock and a dynamic map, its chaotic appearance hiding a perfect mathematical order that only patience and technology could reveal. Beyond the sheer spectacle and the mind-bending orbital mechanics, the true, profound value of these sextuple star systems lies in their role as the universe's ultimate testing grounds. They are not merely curiosities to be observed. They are fundamental physics laboratories operating on a scale and at energy levels we could never hope to achieve in any particle collider or plasma chamber on Earth. Each system presents a unique combination of stellar masses, orbital speeds, and magnetic field strengths, allowing us to probe and stress test different aspects of our theoretical models under the most extreme conditions imaginable. Consider the challenge of gravitational dynamics. For centuries, our understanding was built on the elegant, solvable two-body problem. The moment you introduce a third mass, let alone a sixth, the equations of motion become chaotic and analytically unsolvable. A sextuple system is the most complex, stable configuration of gravitating bodies we know of, a living, breathing manifestation of the infamous n-body problem. By meticulously tracking the motions of these 6 stars over decades, we are essentially collecting a monumental dataset of real-world gravitational interactions. We can watch how subtle perturbations ripple through the hierarchy, how resonances maintain stability, and how energy is transferred between orbits. This isn't abstract math. It's observational data we can feed back into our most powerful supercomputers to refine our simulations of gravity itself, pushing our models to their absolute limits and searching for any tiny deviation that might hint at new physics beyond Einstein's general relativity. The diversity of stellar types within a single system creates a unique opportunity to study stellar evolution in a controlled, comparative environment. Normally, if we want to understand how a star's mass affects its life cycle, we have to compare stars from all over the galaxy, stars that formed at different times from clouds with different chemical compositions. It's like trying to study the aging process by comparing 100 different people from 100 different families with 100 different diets. But in a sextuple system, we have 6 stars that all formed from the same cloud at roughly the same time with the same initial chemical makeup. The only major variable is their mass. This allows for a perfectly controlled experiment. We can directly observe how a massive, hot blue star evolves alongside its lower mass, cooler red dwarf siblings. We can watch as one star in a tight binary begins to transfer mass to its partner, dramatically altering both of their evolutionary paths in real time. It's a side-by-side comparison that would be impossible to arrange otherwise, giving us an unprecedented view into how mass dictates destiny for a star. Then there is the realm of plasma physics and magnetohydrodynamics, the study of how electrically conductive fluids behave in magnetic fields. The space between these stars is not empty. It's a seething, turbulent sea of plasma, shaped by the competing gravitational and magnetic forces of all 6 bodies. When the stellar winds from these stars collide, they create immense permanent shock waves where particles are accelerated to relativistic speeds, generating those powerful X-rays we detect. These colliding wind regions are natural particle accelerators far more powerful than the Large Hadron Collider, allowing us to study high-energy particle physics in a setting we can observe but never recreate. Furthermore, the complex magnetic fields, constantly being wound up and snapping in reconnection events, create a natural experiment in magnetic confinement and energy release, processes that are crucial to understanding everything from nuclear fusion reactor design to the formation of solar flares. By studying this cosmic maelstrom, we are essentially peering into a fundamental physical process that governs the behavior of most of the visible matter in the universe. Each system offers a slightly different experimental setup. One might have an ultra-tight binary of white dwarfs, allowing us to study gravitational wave emission and tidal forces at their most extreme. Another might feature a pair of massive, flaring red dwarfs, perfect for analyzing stellar magnetic activity and superflare mechanics. A third might have a widely separated, quiet binary, ideal for testing the long-term stability of hierarchical orbits. There is no single experiment called a sextuple star system. There is a vast catalog of unique natural laboratories, each configured by nature to challenge a different facet of our understanding. They force us to move beyond idealized, isolated models and confront the messy, interconnected, and gloriously complex reality of how physics operates on a grand scale, providing insights that resonate across all of astronomy and fundamental physics. And so we arrive at the final and perhaps most humbling discovery of all. We've journeyed through the mesmerizing dynamics, the impossible planets, and the cosmic laboratories of these stellar families. We've seen how they can form and, against all odds, survive for billions of years, which leads to an unavoidable, profound question. If they are so stable and so magnificent, why are they almost impossibly rare? In a galaxy brimming with hundreds of billions of stars, we have only confirmed a tiny handful of these sextuple systems. Their scarcity is a deafening silence in the cosmic chorus, a puzzle that suggests our understanding of stellar birth is still missing a crucial piece. The first layer of this mystery is the sheer statistical improbability of their initial formation. For a sextuple system to be born, a single, massive cloud of gas and dust must possess a very specific and unlikely set of properties. It needs to be incredibly dense and massive enough to fragment into not just 2 or 3, but 6 distinct clumps. More importantly, it must have just the right amount of angular momentum, the spin of the cloud as it collapses. Too little spin and everything collapses into a single, messy merger. Too much spin, and the cloud flings itself apart before any stars can form at all. To create a stable hierarchy, the cloud needs a golden mean of rotation, allowing it to fragment in that precise, nested manner, like a set of Russian dolls materializing from chaos. Even if a cloud miraculously meets these conditions, the birth process itself is a perilous gauntlet. The early life of a star system is violent and unstable, filled with gravitational shoves and pulls from sibling stars that are still settling into their orbits. For every one sextuple system that successfully navigates this adolescent turmoil and achieves a stable, resonant configuration, countless others must fail. Computer simulations show that the most common fate for a young group of 6 stars is not a graceful dance, but a gravitational demolition derby. The usual outcome is a series of violent ejections, where 1 or 2 stars are flung out into the darkness of interstellar space at tremendous speeds, becoming forever lost to their family. The rest often collapse inward, resulting in catastrophic collisions that leave behind a single, bizarrely massive star or a brilliant stellar remnant surrounded by debris. The formation of a stable sextuple isn't just unlikely, it's a victory snatched from the jaws of almost certain gravitational chaos. This leads to a haunting possibility. What if these systems aren't actually that rare? What if they form with some frequency, but their very nature makes them incredibly difficult for us to detect? Our primary method for discovering multi-star systems is through eclipses, the telltale dip in light when one star passes in front of another. But for a sextuple system to eclipse from our vantage point, its entire complex orbital plane must be almost perfectly edge onto our line of sight. The odds of that specific alignment for any given system are astronomically low. The vast majority of them would be tilted at some angle, their intricate dances hidden from our view, their composite light appearing as nothing more than a single, unremarkable point in the sky. We might be surrounded by a hidden population of these cosmic wonders, their brilliance and complexity completely invisible to our current search methods, their secrets waiting for more advanced technology to reveal. Perhaps the most sobering thought is that we might be living at the wrong time to see them in their prime. The lifespan of a sextuple system could be measured in stages of stability. They may blaze into existence in a brilliant, brief era of complex harmony, only to be inevitably worn down by the relentless pull of gravitational wave emission. The ultra-tight inner binaries are constantly losing orbital energy, slowly spiraling closer together over hundreds of millions of years. This slow decay could eventually push the entire system across a stability threshold, triggering a final, catastrophic collapse. The systems we see today, like Castor, could be the rare elderly survivors, the last members of a once great population that has mostly already met its end in spectacular mergers or silent dispersions. Their rarity wouldn't be about birth, but about longevity. We are simply witnessing the last few shining examples of a dying breed, the final notes of a symphony that the universe has mostly finished playing. This profound rarity transforms our perspective entirely. Each confirmed sextuple system is no longer just an astronomical object, it is a cosmic miracle. It is a testament to a universe capable of crafting order of breathtaking complexity from chaos, and a reminder of the incredibly specific and fragile conditions that allow such order to persist. They are the ultimate examples of celestial fine-tuning, each one a validation of the physical laws that govern our cosmos pushed to their absolute limit. Their existence against all odds suggests that even in a universe governed by probability and chaos, there is still room for the improbable, the exquisite, and the miraculously stable. They are not merely stars, they are a glimpse into the deepest potential for harmony that the physical world allows, making their fleeting, brilliant lives one of the most valuable and mysterious discoveries in all of space. So as we pull back from this journey through 30 of the strangest discoveries about sextuple star systems, one overwhelming truth becomes clear. The universe is not just more complex than we imagined, but more complex than we can imagine. We began with a single point of light in Gemini and unfolded it into a cosmic epic of 6 stars locked in a gravitational ballet, so precise it defies the very chaos we thought governed all things. These are not mere curiosities, they are profound challenges to our understanding of cosmic architecture. They force us to abandon simple models and embrace a reality where stars can steal from each other, where planets orbit not one sun but six, and where the fabric of spacetime itself is woven into a dynamic kaleidoscope by their immense mass. Each discovery we've explored, from the impossible ages and chemical oddities to the gravitational wave symphonies and magnetic fury, reveals a deeper layer of mystery. Just when we think we have a rule, the universe delivers an exception so spectacular it rewrites the textbook. These systems are living proof that for every question we answer, a dozen new, more fascinating questions emerge. They humble us, reminding us that we are only at the very beginning of comprehending the true depth of cosmic complexity. The existence of such intricate, stable, and ancient systems is a testament to the universe's boundless creativity, its ability to engineer harmony from apparent chaos on a scale that still leaves our greatest minds in awe. This journey doesn't end here, it simply opens a new door. What other celestial marvels are waiting for us, hidden in the light of a seemingly ordinary star? The search continues, and each new telescope, each new algorithm, brings us closer to uncovering secrets we haven't even begun to dream of. The universe is talking, we are only just learning how to listen. Now we want to hear from you. Which of these discoveries completely reshaped your view of the cosmos? Was it the tidally locked stars acting as a cosmic gyroscope, the baffling Sextuple planets, or the incredible magnetic storms that would make our sun's flares look like a tiny spark? Let us know in the comments below which fact amazed you the most. And if you're ready to unravel more mysteries of the cosmos with us, make sure to subscribe and hit the bell so you don't miss our next adventure into the unknown.